Hello, my name is Hussein,
And I'm Al-Bloushi.
and we will be talking about the advances in biosignal processing, ECG, EEG, and EMG analysis for diagnosis and monitoring. The point that we're going to be talking about is the first point is the advances in ECG, EEG, and EMG signal processing. The second thing we're going to be talking about is the clinical implications for diagnosis and treatments. The third, the third thing we're going to be talking about is the noise reduction techniques. The fourth one is the feature extraction, and the last thing is the integration into wearable health monitoring devices.
As my partner mentioned, we'll be talking about biomedical signals, which is a collective electrical signal acquired from any organ that represents a physical variable of interest. So we'll be talking about the ECG, which is a cardiac health assessment, EEG, a neurological condition, and EMG, neuromuscular activity and muscle disorders, as well as the challenges more in this presentation. The first signal we're going to talk about is ECG signal processing. ECG is a non-invasive diagnostic tool that has a massive impact on investigating cardiovascular diseases. It is the most used diagnostic tool for assessing cardiac health. It is also used for surveillance and experimental trials for drugs with known cardiac effects. However, ECG signals are often contaminated by noise such as baseline wonder, muscle artifacts, and power line interface, which can result in inaccurate diagnosis. Recent advancements have focused on improving artifact removal techniques such as wavelet transforms, adaptive filtering, and feature extraction methods for more accurate arrhythmia detection. Some machine learning models have also made significant strides in ECG classification, support vector machines, SVM, and convolutional neural networks, CNN, have shown promise in distinguishing between normal and abnormal heart rhythms with high accuracy. Additionally, real-time ECG monitoring systems have been developed for wearable devices, allowing for continuous heart rate tracking and early detections of arrhythmias. More on it in this presentation. We see in this figure an ECG signal which consists of P waves, QRS complex, T wave, and a rare U that cannot be seen. The first wave in the ECG cycle is the P wave, which makes up the atrial depolarization. It is the atrial contraction initiated by electrical activity. The second wave consists of three distinct waves, which is the QRS. It represents the ventricle contractions. Next is the T wave, which is known as the resting state. It is when the ventricles return to their resting state to restart, which is needed to repeat the cycle. Lastly, the U wave is rarely seen, but when it is seen, it can help identify abnormalities.
Next, we will be talking about the EEG signal processing. The EEG measures electrical activity in the brain, making it essential for diagnosing neurological disorders such as epilepsy, sleep disorders, and even psychiatric conditions. One of the key challenges in EEG signal processing is the presence of artifacts from eye movement and the muscle activity and external electrical noise. Recent approaches using independent component analysis (ICA) and adaptive filtering have improved the extraction of relevant brainwave patterns. As we can see, the different waves for EEG. The first wave is the alpha wave. It occurs when the patient is awake and relaxed with a frequency of 8 to 12 Hz. The second wave is the beta wave. They are usually small and fast with a frequency of 14 to 30 Hz. The third wave is the theta wave. Um, the theta waves occurs in a state of daydreaming or light sleep, and their frequency is from 4 to 7 Hz. And lastly, the delta wave, it has the lowest frequency and a relatively high amplitude, which is from 0.5 to 3 Hz. Recent breakthroughs in seizure detection using deep learning techniques have shown that models like CNN and recurrent neural networks (RNN) can identify seizure events with remarkable precision. Furthermore, the integration of EEG with wearable devices has enabled non-invasive continuous brain monitoring, which is especially beneficial for patients with epilepsy.
The last signal we'll be talking about is the EMG signal. It is used clinically for neurological and neuromuscular diagnosis problems. It is a signal that measures electrical currents generated in muscles during its contractions, representing neuromuscular activities. The signals reflect the electrical activity of muscles and are used to diagnose muscle-related disorders, monitor rehabilitation, and control prosthetics. A major challenge in EMG signal processing is distinguishing muscle activity from electrical noise and other artifacts. Advances in filtering techniques such as the use of adaptive filters and wavelet transforms have enhanced the quality of EMG signals, making them more suitable for clinical use. As we see in the figure in the slide, to perform an EMG test, a needle is inserted into the muscle. The contraction of the muscle fiber produces an EMG wave. Parameters recorded are the amplitude, duration, number of phases, and rise time. Moving on to machine learning algorithms, they are increasingly being used to classify EMG signals, particularly for controlling prosthetic limbs. Recent studies have demonstrated the effectiveness of support vector machines, the SVM that we talked about previously, and neural networks in distinguishing different muscle actions, enabling real-time control of prosthetics. As we previously mentioned, signals are often contaminated by noise, so it has become a necessity to create a novel algorithm aimed at reducing noise in bioelectrical signals such as the ECG, EEG, and EMG. As mentioned, these signals frequently suffer from interface caused by motion, muscle movements, baseline fluctuations, and power line noise, which can mask essential physiological data. Emerging methods such as adaptive filter, wavelet transforms, empirical mode decomposition (EMD), and machine learning techniques are showing significant effectiveness. As we see in this figure, we have an unfiltered ECG signal contaminated by noise and a filtered ECG signal that has removed all of the noise, and we can see the signals more clearly to get a more accurate diagnosis.
Next, we will be talking about the feature extraction. Improvements in algorithms for feature extraction and classification have greatly improved the analysis of biomedical signals such as ECG, EEG, and EMG. These signals are naturally intricate, possessing distinct characteristics that necessitate specialized methods. New algorithms frequently combining machine learning and deep learning are being created to derive significant features like spectral, temporal, and morphological patterns while minimizing noise.
So the integration of wearable health monitoring devices using biomedical signals, it has revolutionized the human welfare. The monitoring of the human body causes immense impact on healthcare and technology involved by effectively and efficiently collecting biosignal and biometrics from the body. It has now become crucial in today's medical field. These technologies help people suffering from seizures For example, an alarm will go off when an onset seizure is about to occur. So this alarm will prevent the patients from an injury from a fall, as well as diabetic patients require constant non-invasive tool in order to monitor their blood sugar every hour. So these are just a few examples of how wearable devices in healthcare has become crucial in modern patient care. As we know, today AI is used in every field. The use of AI in medical care provided real-time learning, data mining, and as mentioned above, machine learning. The use of AI is constantly developing under proper care and research. This would lead to achieving a better recognition and understanding of the state of the human body from raw data records. During this research, we saw the potential of advanced signal processing techniques, particularly in machine learning and deep learning methods, in improving the accuracy and reliability of ECG, EEG, and EMG analysis. These advances allowed for more precise diagnosis, early detection of medical conditions, and enhanced real-time monitoring capabilities. However, we found that the key challenges were improving signal quality in noisy environments and scaling techniques for wearable devices. Future research would focus on refining these algorithms for better efficiency and real-time implementation, as well as exploring hybrid models that integrate multiple biosignals for more comprehensive monitoring.
To conclude, recent advancements in ECG, EEG, and EMG biosignal processing have significantly enhanced diagnostic accuracy and enabled continuous health monitoring. Machine learning, artifact removal, and real time processing are at the forefront of these developments, offering promising solutions for personalized medicine and chronic disease management. Further research into improving the efficiency, real time integration, and wearable device technology will drive the next generation of biosignal based diagnostic tools. Thank you.